Much of history of mathematics is marked by the discovery of special types of numbers. We're thinking about counting numbers, the number zero, negative numbers, irrational numbers. We also think about pi. Pi, you remember, is the circumference divided by the diameter, and imaginary numbers, which is the square root of -1. I am now going to introduce another number called E, or Euler's number, because it's named after Leonhard Euler, who was a Swiss mathematician and engineer. And E is a very special number. It models a variety of situations in which a quantity either grows or decays continuously. We're thinking about money, so we're thinking about compound interest. We're thinking about how drugs are utilized in the body or absorbed in the body. We talk about probabilities or population studies and atmospheric pressure, to name a few. So the first question would be, what is E? Well, E can be defined in a number of ways, and I'm going to show you one of them. So E is approximately the value of 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus continue 1 over 5 factorial, and we're going to continue until we get 1 over n factorial. Now let's just recap what is a factorial. So the word is factorial, and if I tell you 3 factorial, then it's 3 multiplied by 2 multiplied by 1, and 3 factorial has a value of 6. If we talk about, say, 5 factorial, we're going to write down 5 times 4 times 3 times 2 times 1, and this adds up to 120. So 1 over 0 factorial has a value of 1. 1 over 1 factorial has a value of 1. 1 over 2 factorial, 2 factorial is 2 times 1, so it's 1 over 2 or a half. We know that 3 factorial is 6, so 1 over 3 factorial gives you 1 over 6. And 1 over 4 factorial will be 1 over 24, and we know that 5 factorial has a value of 120, so 1 over 5 factorial is 1 over 120 plus 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 right up to 1 over n factorial. And if you take, say, 100 of these factorials, or then maybe add up 1,000 of these factorials, and then maybe add up 1,000,000 of these factorials, you get closer and closer and closer to the number 2,7182,8182,459, etc. This is an irrational number, and this is the value of E. I also went onto the Math is Fun website, and I found a lovely little rhyme to help you to remember the first 10 numbers of E. So it says, to express E, remember to memorize a sentence to simplify this. So we count the letters in the word. So 2, so it'll be 2, comma, express has 7. E is 1 letter, remember, is 8. 2 is 2, memorize is 8, then we get 1, then we get 3, 6, 7, 8, 2, etc., etc., etc. And so these are the first 10 digits of E. So when we draw the graph of E to the x, we call it the natural exponential function. And I've drawn a table here, and I've chosen certain x values from -2 to 3, and then I've worked out the y coordinate. So the first thing we did is we substitute e to the -2, because we're drawing the graph of f of x equals to e to the x, and x equals to -2. So if you enter this on a calculator, you get 0,1353352,832. And then I've just rounded it off to 1 decimal place to help me to draw the graph, so it's approximately equal to 0,1. I continue in this way, and I substitute x equals to -1, and then I substitute x equals to 0, and then we know that e to the naught, so if my base is e and my exponent is 0, I'm going to get the value of 1. And then E, we know is 2,7182818248. So I get 2,7, and I continue in this way, and we draw the graph. So here we have the sketch of f of x equals to e to the x. And it is an exponential graph. It has a y-intercept at x is 0 and y is 1. It has an asymptote along the x-axis, so your asymptote is the line y equals to 0. We see that when x is negative 2, then my y value is going to be approximately 0, 1. We see that when x is 1, then my y values is going to be 2,71828, etc. But I write it as, in this case, just to draw the graph very inaccurately. But when x is 1, I have y is 2,7. Right, so here we have the graph of y equals to e to the x, and I'm comparing it to the graph y equals to 3 to the x and y equals to 2 to the x. Y equals to 3 to the e to the x, is the red graph, and you see it lies between the graphs of y equals to 2 to the x and 3 to the x, and this makes sense because the value of e is going to be, so if I have y equals to e to the x, I am actually drawing the graph of 2,71828 to the x. And the number 2,7 is between 2 and 3. And as with all exponential graphs, we have an intercept on the y-axis at x equals to 0 and y equals to 1. And we see that the range is always positive, so the range will be, y will be all numbers greater than 0, not equal to 0, because you have an asymptote along the x-axis, so your asymptote is the line y equals to 0. We're now extending our knowledge to the log. So if I take the log of a number x to the base e, then I have what is called the natural log, and I write it as ln e, ln, sorry, not ln e, ln x, and ln ln x for natural log of x. And as with the logs that we've discussed earlier, when we had the common log or the log to any base, the logarithmic rules apply to the natural log as well. So we've discussed these rules using the common log and the log to any base a, and they apply to the natural log. So the ln of xy equals to the ln of x plus the ln of y. So what I'm saying is that if I take log of xy to the base e, it is going to equal to the log of x to the base e plus the log of y to the base e, and the log to the base e of any number is called ln of that number. So the product rule applies. The quotient rule works as well, so ln of x divided by y is going to be ln of x minus ln of y. The power rule will work too, so ln of x to the n is n ln x. So we know that log of a to the base a equals to 1. So it is natural that if my base is e, and I'm finding the log of e to the base and the number have the same value. So the log of e to the base e has a value of 1. So this is why ln of e equals to 1. Also, it states here that ln of 1 equals to 0. And the reason why is if I've got log of 1 to the base e, that value is 0, because the ln, or the log of 1, the log of 1 to any base has a value of 0. So whether your base is e, or your base is 10, or your base is 2, it doesn't matter what your base is, the log of 1 to that base will always equal to 0. Also, we see that the ln of 1 over x equals to the ln minus ln of x. So if I take the left-hand side, and the left-hand side is ln, or the log to base e of 1 over x. Now 1 over x can be written as x to the negative 1. And if you apply the power rule, which says that the ln of x to the n equals to n ln x, so I take my 1, and using the power rule, it now becomes a coefficient. So it's going to be minus 1 ln x.